close your eyes for just a moment. Imagine you are floating, not falling, floating. There is no ground beneath you, no sky above you. There is only darkness, and within that darkness, a silence so complete that it feels like the universe itself has stopped breathing. Now, slowly, open them. In front of you, far, impossibly far, there is a light, just one, small and faint, like a single ember left from a fire that burned billions of years ago. And then, as your eyes adjust to the dark, you realize it isn't one light. It's thousands, millions, entire rivers of stars stretching from one edge of everything to the other. You are somewhere between galaxies, somewhere no human being has ever been, and perhaps no human being will ever go. And yet, here you are. This is where our journey begins tonight, not with facts and figures, not with equations written on a classroom blackboard. Tonight, we begin with a question so simple that a child could ask it, and so deep that the greatest minds in human history have spent their entire lives trying to answer it. What if there were a shortcut, not a shortcut across a city, or even across a country, a shortcut across the universe itself, a tunnel hidden somewhere in the fabric of space and time that could carry you from one end of existence to the other in the space of a single breath. Physicists have a name for this tunnel. They call it a wormhole. And the strange, almost unsettling truth is this: there is nothing in the laws of physics that says it cannot exist. For decades, scientists have debated whether wormholes are real structures woven into the cosmos, or simply beautiful equations with nowhere to go. But in recent years, something has shifted. New discoveries, new theories, new observations have begun to suggest that what we once thought of as pure science fiction may be woven into the very architecture of reality. Tonight, we are going to travel through that question together, slowly, carefully, as if we were walking through a great dark forest, pausing at every clearing to look up at the stars and ask, what is this place? How did it get here? And where could it take us? But before we go any further, there is something you should know about wormholes. They are not just tunnels through space. They are, if they exist, tunnels through time itself, which means that traveling through one would not simply move you from one star to another. It could, in theory, move you from one moment to another, forward, backward, to an era of the universe when stars were just beginning to form, or to a moment so far in the future that everything we know has long since gone cold and dark. Does that sound impossible? Good. Hold that feeling, because tonight, the impossible is exactly where we are going. Let the darkness outside your window become the darkness between galaxies. Let the quiet sounds around you become the silence of deep space. And let your mind, for just a little while, become something that does not need to rush, does not need to arrive, does not need to understand everything all at once. Tonight, we travel slowly, and we travel far. There is a soft kind of wonder that comes from sitting with a question you cannot fully answer, a feeling that is part curiosity and part peace, as if the not knowing itself is a kind of gift. That is the feeling we are chasing tonight. Not the answer, the journey. Because when you ask the question, what if you traveled through a wormhole, you are really asking something much larger. You are asking, what is the universe truly beneath everything we think we know about it? What are the rules? And are those rules written in stone? Or are they somewhere out there in the dark, already bending? Somewhere in the universe right now, or so some physicists believe, there may be a place where space folds back on itself, where 2 points that are unimaginably far apart are suddenly, quietly, impossibly close, where the long, cold distance between stars collapses into something a single step could cross. And perhaps, just perhaps, there is something waiting on the other side. Let's find out what it might be. Before we go any further into the dark, let's take a moment to understand what this journey is actually going to give us. Tonight is not about memorizing facts. It is not about passing a test or reciting the names of equations. You will forget by morning. Tonight is about something rarer and more valuable than any of that. Tonight is about seeing the universe differently. Over the course of the next 2 hours, we are going to travel through one of the deepest and most beautiful mysteries in all of science. We are going to ask what a wormhole actually is, not just as a word, but as a real physical structure. We are going to explore where they might exist, how they might form, and why the same equations that predicted black holes, objects we once thought were fantasy, but have now photographed with our own technology. Those same equations tell us that wormholes may be just as real. We are going to ask what it would actually feel like to travel through one. Not in the way a physics textbook would describe it, but in the way a poet or a dreamer might. What would you see? What would you sense? Would there be light? Would there be darkness? Would time feel different? Would you arrive at the other end the same person who stepped in? And then, this is where it gets truly remarkable. We are going to explore what wormholes might tell us about the deepest nature of reality itself. Because in recent years, something extraordinary has happened in theoretical physics. Scientists have begun to find connections between wormholes and quantum mechanics, the mysterious set of rules that governs the behavior of the smallest particles in the universe. And those connections have led to ideas so strange, so beautiful, so fundamentally world-altering, that even the scientists who discovered them had to sit down and catch their breath. But that isn't the strangest part. The strangest part is that wormholes, if they exist, may not simply be tunnels through space. They may be, according to some of the most cutting-edge theories in physics today, fundamental to the very reason space exists at all. The reason that you and I and every star and planet in the observable universe are connected to each other in the first place may have something to do with these hidden tunnels in the fabric of reality. We are also going to explore the question that perhaps fascinates people most. Could a wormhole be used to travel through time? And if so, what would that mean? Not just for the science fiction stories we love, but for the actual structure of cause and effect in the universe, for the nature of choice and consequence, for what it means to exist in time at all. Every section of tonight's journey will end not with an answer, but with a deeper question. That is the nature of this particular mystery. The more you understand about wormholes, the more you realize how much is still unknown. And that is not a frustrating thing. It is one of the most beautiful things about the universe. It is always more complex, more strange, and more wonderful than we are currently capable of imagining. What you will feel by the end of tonight is not the satisfaction of having solved a puzzle. It is something better than that. You will feel the particular peace that comes from having sat quietly with a great mystery and having let it expand around you, and having realized that being surrounded by questions you cannot answer is not a frightening thing at all. It is, in fact, one of the most comforting feelings available to a human being, because it means the universe is larger than you. And there is something deeply restful about that. So settle in. Let your breathing slow. Let the room around you become a little quieter, a little further away. We are about to step through the door. Every great mystery in science begins with a single moment. A moment when someone looked at the world and said, "What if there's something here that nobody has noticed yet?" For wormholes, that moment came in the early 20th century. And it came not in a laboratory filled with equipment, but in the quiet of a mind that was simply following mathematics to wherever it led, regardless of how strange the destination turned out to be. The year was 1916. The world was at war, and a physicist named Karl Schwarzschild, stationed at the Russian front, was solving the equations that Albert Einstein had published just 1 year earlier. Einstein's theory of general relativity had just changed everything. It had replaced the old Newtonian idea of gravity, a force reaching across space, with something stranger and more beautiful. The idea that massive objects bend the fabric of space and time around them, and that what we call gravity is simply the path that everything naturally follows through that curved space. Einstein's equations were extraordinary, but they were also extraordinarily difficult to solve. Schwarzschild, working in the middle of a war, surrounded by noise and danger, found a perfect solution, a clean, exact solution. And within that solution, he discovered something nobody had expected. He found a point, a specific location in his mathematics where something went wrong, where his equations produced not just very large numbers, but infinity itself, a singularity, a place where the known laws of physics simply broke down. At first, most scientists assumed this singularity was a mathematical curiosity, an artifact of the equations, not a real feature of the physical universe. Surely, they thought, nothing in nature could be that extreme. Surely the universe would not actually allow a place where density became infinite, where space and time collapsed into something beyond description. They were wrong. What Schwarzschild had found was the first mathematical description of what we now call a black hole. But that wasn't the strangest part. Several years later, as physicists began to understand Schwarzschild's solution more deeply, they made a discovery that nobody had anticipated. When you look at the full geometry of space around a black hole, not just the outside, but the complete mathematical structure, you find something remarkable. On the other side of the singularity, the equations describe another region of space, a separate region connected to our universe through the black hole itself. Imagine a sphere. Now imagine that the inside of that sphere is not a closed, empty space, but a tunnel, a throat that leads not to another part of the sphere, but to another sphere entirely, another place, another region of space-time. The first person to describe this structure clearly was an Austrian physicist named Ludwig Flamm in 1916. He called it a white hole, a region where, instead of things being pulled in, they would be pushed out, a mirror image of the black hole. But the full, beautiful picture didn't emerge until 1935, when Albert Einstein himself and his colleague Nathan Rosen sat down together and worked through the mathematics completely. What they found was that a black hole, properly described by the equations of general relativity, is not a dead end. It is a passage, 2 points in space-time, connected by a bridge. They called it an Einstein-Rosen bridge. We call it a wormhole. And here is what is important to understand. Einstein and Rosen were not trying to invent a shortcut through the cosmos. They were not writing science fiction. They were simply following their equations to their logical conclusion. The bridge was not something they put into the mathematics. It was something they found there. The universe, at least as general relativity describes it, appears to contain these structures. They seem to be baked into the geometry of space itself. Yet another mystery emerged immediately. Just because the equations permit something does not mean it actually exists in physical reality. And even if wormholes do form, perhaps at the centers of black holes, or in the conditions immediately after the Big Bang, or at the quantum scale where space itself may be foamy and riddled with tiny tunnels, the question of whether they could be traversed was still completely open. Could you actually travel through one? Or would the tunnel collapse the instant anything tried to pass through it? To understand the answer, we need to go deeper, much deeper. Because the stability of a wormhole depends on something that sounds, at first, almost like it comes from the imagination of a philosopher rather than the laboratory of a physicist. It depends on the existence of something called negative energy. Not negative in the sense of being harmful or dark. Negative in a very precise, technical, physical sense. Energy that pushes outward rather than pulling inward. Gravity, remember, pulls. Everything in our everyday experience pulls. The force that holds galaxies together, that keeps planets in their orbits, that makes an apple fall from a tree. All of it is attractive. It draws things together. But the equations of general relativity permit the existence of a form of energy that does the opposite, a form of energy that repels, that expands, that pushes the walls of a tunnel outward, rather than letting them collapse inward. If you could line the throat of a wormhole with enough of this negative energy, you could keep it open. You could stabilize it. You could, in principle, walk through. Does negative energy actually exist? Scientists soon discovered that the answer is yes, but barely. In the 1940s, a Dutch physicist named Hendrik Casimir predicted that two perfectly flat, perfectly parallel metal plates placed very close together in a vacuum would experience a tiny, attractive force, not because of gravity, And not because of electromagnetism, but because of the quantum nature of empty space itself. Empty space, it turns out, is not empty. It seethes with quantum fluctuations, momentary, ghost-like appearances and disappearances of particle-antiparticle pairs. These fluctuations occur everywhere, all the time, at every point in the universe. But between two very closely spaced plates, some of the fluctuations are excluded. The wavelengths are too long to fit between the plates. And that exclusion creates a region where the energy density is actually lower than it is in a surrounding vacuum. Lower than nothing, negative, by any reasonable definition. This effect was confirmed experimentally in 1997. Negative energy is real. It exists. It can be created, at least in principle. But here is the problem, and it is a significant one. The amount of negative energy created by the Casimir effect is extraordinarily small. Smaller than anything a human being could work with meaningfully. And the calculations suggest that to keep a traversable wormhole open, a wormhole large enough for a person to pass through, you would need a quantity of negative energy comparable to the total energy output of several suns. It may be one of the greatest engineering challenges in the history of physics. But notice what the physics is not saying. It is not saying it's impossible. It is saying it's difficult, perhaps unimaginably difficult, perhaps beyond anything human civilization could achieve for thousands or millions of years, but not forbidden, not impossible in principle. The laws of physics, as far as we currently understand them, do not prevent wormholes from being traversable. They simply make it very, very hard. And this is where things become even more fascinating. Because if you follow the logic of traversable wormholes, the next question arrives almost immediately. And it is even more extraordinary than anything we have discussed so far. If you can travel through a wormhole, if you can move from one point in space to another in an instant, or near instant, then given what we know about the relationship between space and time in Einstein's universe, you might also be able to do something else, something that sounds at first completely impossible. You might be able to travel through time. We will explore that in a little while. But first, we need to understand something more fundamental. What it would actually feel like to approach a wormhole. What you would see, what the universe would look like from the inside of one. Because the visual experience of a wormhole, according to the physics, is unlike anything else in the cosmos. Close your eyes again just for a moment. You are drifting through deep space. Around you, in every direction, stars. The Milky Way arcs across the sky like a river of frozen light. Not the pale smudge we see from Earth's surface, blurred by atmosphere and city glow, but the full, overwhelming brilliance of 200 billion stars seen all at once. The sky is not black. It is deep blue-violet, filled from edge to edge with light that has traveled for thousands of years to reach your eyes. And then, ahead of you, you see something. At first, it looks like a hole, a perfectly circular absence in the star field, a darkness that seems too precise to be natural. Not the darkness of space, which has its own subtle texture, its own depth. This darkness is different. It is bordered by light that bends around it in impossible curves, as if the photons themselves are unsure whether to go in or stay out. You are looking at a wormhole. The visual experience of a wormhole is something that physicists have actually calculated using the equations of general relativity, and the picture those equations paint is breathtaking. The first thing you would notice is the lensing, because a wormhole is, at its heart, a curved structure in space-time. Light passing near it would be bent, dramatically bent. The stars behind the wormhole would appear distorted, stretched, and warped into rings and arcs around its edges, the way a lens distorts the objects seen through it. But this lens would be made not of glass, but of space itself. And here is the truly remarkable thing. If you looked directly into the center of the wormhole, you would not see darkness. You would see light coming from somewhere else entirely. If the other end of the wormhole were in a different part of the galaxy, or a different galaxy altogether, light from that distant place would be traveling down the tunnel toward you. And as you approached, that light would become brighter, more complex, more detailed. You would see stars you had never seen before, constellations that no human eye has ever mapped, light that has never touched the earth. The wormhole's opening would look, to your eye, like a perfect sphere. Within that sphere, you would see a compressed, distorted, but recognizable image of whatever place the other end opens onto. If the other end were near a nebula, one of those vast, glowing clouds of gas and dust where new stars are born, you would see colors in the opening that have no name in any human language. Magentas and electric blues and soft golden greens, all folded together by the gravitational lensing into shapes that no painter has ever attempted. Around the edge of the opening, the light from your own region of space, the stars behind you, would be stretched into a thin, bright ring, a perfect halo, as if the wormhole were wearing a crown of your home universe. Scientists soon discovered that the precise appearance of a wormhole would depend on what kind of wormhole it was. The simplest kind, the kind described by Schwarzschild's original solution, would be almost impossible to see clearly from a distance because it would be hidden inside a black hole. You would approach the black hole, pass through its event horizon, and only then find the entrance to the tunnel. But a traversable wormhole, the kind that some physicists have theorized could exist in nature, or could theoretically be constructed, would be different. It would sit in space like an open door, visible, accessible, waiting. Now imagine you decide to approach it. As you draw closer, the sphere in front of you grows larger, filling more and more of your visual field. The stars around its edge stretch and multiply. The light from the other side becomes more detailed. You can begin to make out individual stars in the distant view through the opening. They look slightly different from yours. Their colors are subtly off. You notice, with a strange feeling of vertigo, that the sky visible through the wormhole has a slightly different texture from the sky around you. More red, more ancient. You are looking at a part of the universe you have never seen. And then you cross the threshold. This is where things become very strange indeed. Inside the throat of a traversable wormhole, you would be in a region of space-time unlike anything else in the cosmos. The geometry around you would be profoundly distorted, not dangerously, not like the extreme tidal forces near a black hole's singularity, which would tear any object apart, but noticeably. Directions would feel wrong, not disorienting in the way that being lost in a forest feels wrong, but geometrically wrong. The concept of forward and backward would behave unusually. Light around you would behave in ways that defy every intuition developed over a lifetime of living in flat, Euclidean space. And the view behind you, back toward where you came from, would begin to look the way the wormhole looked when you first saw it from the outside. The image of your home region of space would compress into a perfect sphere behind you, surrounded by distorted, stretched light. You would be simultaneously looking at where you came from and where you are going, both compressed into two spheres on opposite ends of a tunnel that, in a very real mathematical sense, has no length at all. Transit time through an idealized traversable wormhole could be nearly instantaneous, or it could take minutes or hours, depending on its structure. But during that time, you would be in a place that is, in a profound sense, neither here nor there. You would be in the throat of reality itself. What happened next surprised the physicists who first calculated it. When you emerged on the other side, you would not simply appear in a new location. You would appear with a view of the universe that had been impossible to have before. You would be able to look back through the wormhole and see, perfectly clearly, the exact location you had come from. The two ends of the tunnel would remain connected. If you stood at one end and looked in, you would see, at the other end of the tunnel, someone standing at the other entrance, looking back at you. It would be like looking down a hallway that was, from the outside, a single step across. The answer raised an even bigger question. What would this kind of travel do to your experience of time? General relativity tells us that time is not the same everywhere. Clocks run slower in strong gravitational fields. Clocks run slower for objects moving at high speeds, and wormholes, connecting two points that might have very different gravitational environments, could do something extraordinary to the flow of time between their two ends. If one mouth of a wormhole spent time near a massive object, a neutron star, say, or even a black hole's outer regions, while the other mouth remained in open space, the two ends would age differently. Time at the first mouth would flow more slowly. And when you traveled from one end to the other, you wouldn't just cross space, you would cross time. But that is a story for another section of our journey. For now, let yourself sit with the image, a perfect sphere hanging in space, framed by the light of 1,000 distorted stars, opening onto a view of somewhere else entirely. Something that looks, for all the world, like an eye. An eye that the universe has opened, gazing from one corner of itself to another. There is a question that sits quietly at the center of everything we have explored so far, and it is time to face it directly. Is any of this actually possible? Not in the abstract, philosophical sense. Not as a thought experiment, but physically, materially, in the actual universe we inhabit. To answer that, we need to understand something about the nature of physical law. Because when physicists say something is possible, they mean something very precise. They mean there exists no known law of physics that forbids it. And here is the remarkable thing about wormholes. There is no such law. Let us walk through the physics carefully, not with equations, but with images and ideas that will let you feel what the physics actually describes. General relativity is, at its heart, a theory about the shape of space-time. It says that the presence of mass and energy bends space. A massive star bends space around it, creating the curved paths that planets follow. An even more massive object, a neutron star, a black hole, bends space so severely that those curved paths spiral inward, closing off. Nothing can escape. But general relativity is not a theory about what puts mass and energy into space. It is a theory about what mass and energy do once they're there. And this means that if you want to know what kinds of space-time geometries are permitted by general relativity, you simply have to ask, what kinds of mass-energy distributions would produce that geometry? When physicists applied this logic to wormholes, they found something fascinating: a traversable wormhole, one with a stable, open throat, would require a distribution of energy that was, in certain regions, negative. Specifically, the energy density near the throat of the wormhole would need to be below zero, below the vacuum, lower than empty space. We have already encountered this concept: negative energy. The Casimir effect demonstrates that it exists. Quantum mechanics, with its seething vacuum full of fluctuations, permits negative energy as a real physical quantity. But here is where the difficulty lies. The amount of negative energy required to keep a wormhole open scales with the size of the wormhole. A microscopic wormhole would require a relatively small amount of negative energy. But a wormhole large enough for a person to pass through, say 2 meters across, would require a quantity of negative energy that, by some estimates, would be comparable to the energy of an entire Jupiter-mass planet, but negative. Where does that energy come from? How could it be assembled? Could it be naturally occurring? Scientists soon discovered that there might be ways around this problem. Not easy ways. There are no easy ways in this corner of physics, but potentially real ones. One approach involves what physicists call exotic matter. This is not the exotic matter of science fiction, glowing, mysterious substances from distant civilizations. Exotic matter in physics simply means matter with properties that are unusual or counterintuitive. Matter with negative energy density would qualify. Some theoretical models of certain quantum fields suggest that they could naturally adopt states with negative energy density, at least in specific geometric configurations. Another approach, developed in the 1980s by theoretical physicist Kip Thorne, who later won the Nobel Prize for his work on gravitational waves, and his student, Michael Morris, explored the minimum requirements for a traversable wormhole. Thorne and Morris wanted to know, what is the least exotic thing you would need to keep a wormhole open? What they found was both encouraging and sobering. The wormhole could, in principle, have a very thin region near its throat where negative energy was required, and the rest of the structure could be made of perfectly ordinary matter, or even be empty of matter entirely, the negative energy would only need to exist in a very specific, concentrated region. This was encouraging because it suggested that nature might not need to manufacture enormous quantities of exotic matter throughout the entire wormhole. It would only need to concentrate it where it mattered most. But it was sobering because even this minimum requirement represented something far beyond any technology currently conceivable by human civilization. And this is where things become even more fascinating, because the question is not only whether humans could build a wormhole. The question is also whether nature might have already built them. In the very early universe, in the first fractions of a second after the Big Bang, conditions were unimaginably extreme. Temperatures and densities beyond anything that has existed since. Quantum effects that we do not yet fully understand. The universe was not a calm, structured place. It was a storm of energy and possibility. Some theoretical physicists have proposed that in those extreme conditions, tiny wormholes might have formed naturally. Quantum wormholes, far smaller than an atom, threading through the fabric of space-time in vast numbers. These microscopic wormholes would not be traversable by any macroscopic object, but they might represent something profound about the fundamental structure of space itself. The idea goes like this. Perhaps space, at the very smallest scales, the Planck scale, which is about 10 trillion times smaller than a proton, is not smooth and continuous, as it appears to us at everyday sizes. Perhaps, at that scale, it is foamy, riddled with quantum fluctuations. And perhaps among those fluctuations, tiny wormholes constantly appear and disappear, connecting distant points for a fraction of a moment, before collapsing back into the quantum vacuum. This picture of space, called quantum foam, was first proposed by physicist John Wheeler in the 1950s. And while it has never been directly observed, it is consistent with what we know about quantum mechanics and general relativity. If quantum foam is real, then wormholes are not exotic exceptions to the laws of physics. They are permanent features of space itself, at every point, at every moment, simply too small to interact with anything at our scale. The question would then become not whether wormholes exist, but whether they could be enlarged. Could you take a quantum wormhole and, using the right combination of energy and matter, expand it to human scale? The answer raised an even bigger question. Even if you could, would it remain stable long enough to be useful? This brings us to what may be the most important theoretical result in the entire field of wormhole physics. In the 1990s, physicist Matt Visser showed that certain specific types of wormholes, ones he called thin shell wormholes, could be constructed using a minimum of exotic matter, concentrated in a thin shell around the wormhole's throat. These structures would be mechanically stable, in the sense that small perturbations would not cause them to collapse immediately. But there was still the question of quantum stability, the question of whether the very act of sending radiation, light, particles, information, through the wormhole would create a feedback loop of quantum effects that would ultimately destroy it. This remains unresolved. It is one of the most active areas of theoretical physics today, and that unresolved question is precisely what makes this field so alive, so full of energy, so full of the particular excitement of standing at the edge of the unknown. Somewhere in the mathematics of the universe, there may be a structure that connects two places that are incomprehensibly far apart, and the question of whether we will ever understand it well enough to know whether it could be real. That question keeps physicists awake at night in the best possible way. We have arrived at the question that, more than any other, captures the imagination when the word wormhole is spoken. Can they be used to travel through time? The answer, according to the physics, is yes. But the story of how and why is stranger and more beautiful than any simple yes or no could suggest. To understand it, we need to first understand something about time that is easy to forget in the flow of daily life. Time is not the same everywhere. It is not a universal constant ticking at the same rate across all of space. It is, like space itself, a fabric, a dimension that can be stretched, compressed, curved, and distorted by mass, energy, and motion. Einstein understood this. His special theory of relativity, published in 1905, showed that time passes more slowly for objects moving at high speeds. This is not a metaphor or an analogy. It is measurable, real. The clocks aboard satellites in orbit run at slightly different rates than clocks on the ground, and engineers must account for this when calculating GPS positions. His general theory of relativity, published 10 years later, showed that time also passes more slowly in strong gravitational fields. A clock placed near a massive object, a star, a black hole, will run more slowly than a clock far from any mass. Now, bring these two facts together and consider what happens to a wormhole. Imagine a wormhole with two mouths. Call them mouth A and mouth B. At the moment they form, or at the moment we first create the scenario, they are synchronized. Time at mouth A and time at mouth B are in perfect agreement. Now, imagine that we take mouth B and move it very quickly, close to the speed of light. We accelerate it, carry it across a great distance, then bring it back. The journey takes 10 years by our clock, standing still with mouth A. But because of special relativity, time on the moving mouth passes more slowly. Mouth B, by the time it returns, has only aged 1 year. It has only experienced 1 year of time, while mouth A has experienced 10. The two mouths are no longer synchronized. They are 9 years apart. And here is the extraordinary consequence. If you now step through the wormhole from mouth A to mouth B, you do not just travel across space, you travel back in time by 9 years. Because mouth B is 9 years younger than mouth A. The tunnel connecting them is a shortcut, not just through space, but through those 9 years of time. Scientists soon discovered that this effect could be achieved through gravity as well as motion. If one mouth of the wormhole spends time near an extremely massive object, a neutron star, or the region outside a black hole, while the other mouth remains in open space, the same desynchronization occurs. The mouth near the massive object ages more slowly. and the wormhole becomes a time machine. What happened next in the history of this idea surprised even the physicists who had been thinking about it most carefully. Kip Thorne, the same physicist who had analyzed the requirements for traversable wormholes with his student, Michael Morris, published a landmark paper in 1988 in which he and his collaborators analyzed the time machine scenario in detail. They were trying to understand whether time travel via wormhole was consistent with the known laws of physics, or whether some mechanism would inevitably prevent it. What they found was troubling, not because the laws of physics clearly prohibited time travel through wormholes, but because they clearly did not prohibit it, and the implications were deeply strange. The most obvious problem is what physicists call the grandfather paradox. If you can travel backward in time, what prevents you from going back and changing something that would alter the very circumstances that led to your time travel? The classic form of the paradox. If you traveled back in time and prevented your own grandfather from meeting your grandmother, you would never be born. But if you were never born, you could not travel back in time. But if you did not travel back in time, your grandfather would have met your grandmother, and you would have been born. This logical loop seemed to present a fatal problem for any theory of time travel. But here is where things become genuinely profound. One of the most beautiful proposed resolutions to the grandfather paradox comes not from general relativity, but from quantum mechanics. In the quantum theory of many worlds, a legitimate, if controversial, interpretation of quantum physics, every possible outcome of every quantum event actually occurs, but in separate, branching versions of reality. When you make a decision, both choices happen in different branches of the wave function. If this interpretation is correct, then when you travel back through a wormhole and make a change, you do not change your own past. You branch off into a new version of reality, a parallel universe where the change you made has its full consequences. Your original timeline remains intact. The paradox dissolves. The answer raised an even bigger question. If wormholes connect not just distant points in space, but potentially different branches of the quantum multiverse, then what are they, really? Are they simply passages through space and time, or are they something far more fundamental? We will return to this question, but first, there is another proposed resolution to the time travel paradox, one that does not require parallel universes, and which was formulated by Stephen Hawking in a particularly provocative way. Hawking proposed what he called the chronology protection conjecture. This was not a proven theorem, it was a hypothesis, but it was an elegant one. Hawking argued that the laws of physics, while not explicitly forbidding time travel, contain a built-in mechanism that prevents it in practice. Specifically, he suggested that any time machine, any wormhole configured to allow backward time travel, would be destroyed by quantum effects before it could be used. Here is the mechanism. As the wormhole is tuned to connect two different moments in time, radiation entering the wormhole from one mouth would exit the other mouth in the past, travel to the first mouth again, enter the wormhole, exit in the past, and so on, cycling endlessly, building up in intensity with each loop. The radiation would form a feedback loop that would grow without limit, ultimately destroying the wormhole before any macroscopic object could travel through it. Nature, in Hawking's view, would always protect causality. The universe would not permit time machines. But here is the remarkable thing about Hawking's conjecture. It is a conjecture, not a theorem. It has never been proven, and in the decades since he proposed it, several physicists have found specific wormhole configurations in which the quantum feedback effects appear to be manageable, where the feedback does not grow without limit, and where the wormhole remains stable even when configured as a time machine. The question is still open, and that openness, that profound, beautiful uncertainty at the edge of everything we know about time and space, is perhaps the most honest thing physics can offer us. The universe may permit time travel. It may not. We do not yet know. And there is something quietly wonderful about living at a moment in history when the answer to the question, can we travel through time, is genuinely, honestly, scientifically, we are still finding out. We have been speaking mostly about wormholes as things that might be built, theoretical structures, engineered to precise specifications, requiring exotic matter and human intention. But there is another possibility, one that is, in some ways, even more remarkable. What if the universe has been building wormholes on its own, all along? This is not a fringe idea. Some of the most respected theoretical physicists in the world have seriously explored the possibility that wormholes are not exotic, exceptions to the laws of nature, but natural features of the cosmos, structures that form spontaneously under certain conditions, the way stars form from collapsing clouds of gas, or the way black holes form from dying stars. The most obvious natural candidate is the black hole. We already know that the mathematical description of a black hole, the Schwarzschild solution that Karl Schwarzschild found on the Russian front in 1916, contains, within its full geometric structure, something that looks like a wormhole. The Einstein-Rosen bridge, two regions of space-time connected by a tunnel. But classical black holes, the kind described by the simplest version of general relativity, have a problem. The wormhole inside them is not traversable. It forms and then almost immediately collapses, in a time so short that nothing, not even light, could travel through it before it pinches shut. A classical black hole is a one-way door, not a passage. Yet another mystery emerged when physicists began to ask, what about charged black holes, or rotating black holes, the kind that actually exist in nature? Most real black holes are not the simple, spherically symmetric objects of Schwarzschild's solution. Real black holes rotate, sometimes very rapidly. A rotating black hole is described by a different mathematical solution, called the Kerr metric, found by New Zealand mathematician Roy Kerr in 1963. And the geometry of a Kerr black hole is dramatically different from a Schwarzschild black hole. Inside a rotating black hole, the singularity is not a point, it is a ring. And the mathematics of the Kerr metric, explored fully, reveals pathways through the interior of the black hole that do not necessarily end at the singularity. Paths that, if you followed them in the equations, would carry you through the ring singularity and out somewhere else. Where? The mathematics says another universe, or another region of our own universe, or another time. The equations are frustratingly ambiguous, not because they are wrong, but because they are so complete that they describe scenarios our intuition simply cannot contain. Scientists soon discovered that this was not a defect of the Kerr metric. It was a feature. The rich, complex interior of a rotating black hole was the full, self-consistent picture of what extreme space-time curvature actually produces. And what it produces looks, in the mathematics, like a network of connections, passages from one part of space-time to another. But here is the critical question. Are these mathematical passages physically traversable? Or are they, like the Einstein-Rosen bridge of the Schwarzschild black hole, unstable structures that collapse before anything can cross them? The honest answer is that we do not know. The interior of a black hole is, by definition, a region from which no information can reach us. We cannot observe what happens inside. We can only infer it from theory, and our theories, general relativity alone, without the quantum corrections that would be necessary near a singularity, may not be telling us the complete truth. This is one of the central challenges of modern physics. We have two extraordinarily successful theories: general relativity, which describes the large-scale structure of the universe, and quantum mechanics, which describes the behavior of subatomic particles. And they are, in a precise technical sense, incompatible with each other. They produce contradictions when applied to the same extreme situation. The interior of a black hole is exactly such an extreme situation. Near the singularity, both quantum effects and extreme gravity are relevant simultaneously. We need a theory of quantum gravity to describe what happens there, and we do not yet have one. But we are making progress, extraordinary progress. What happened next surprised the physics community. In 2013, two theorists named Juan Maldacena and Leonard Susskind published a paper that proposed something remarkable. They suggested that there might be a fundamental equivalence between two things that had previously seemed completely unrelated. On one side, wormholes, geometric tunnels connecting distant regions of space-time. On the other side, quantum entanglement, the mysterious phenomenon in which two particles, no matter how far apart, share a quantum state in a way that appears to allow instantaneous correlation between their properties. Maldacena and Susskind proposed that these two phenomena might be the same thing, viewed from different perspectives. Their paper had a simple, striking title: ER equals EPR. ER stood for Einstein-Rosen, the wormhole. EPR stood for Einstein, Podolsky, and Rosen. The quantum entanglement paper that Einstein had published in 1935. The same year, he and Rosen described the wormhole. Both papers were published by the same author in the same year, from two completely different corners of physics. And Maldacena and Susskind were proposing that they were describing the same underlying phenomenon. If ER equals EPR is correct, if wormholes and entanglement are truly the same thing, the implications are staggering. It would mean that Every pair of entangled particles in the universe is connected by a microscopic wormhole. It would mean that quantum entanglement, the mysterious, spooky correlation that Einstein famously called spooky action at a distance, is not mysterious at all. It is simply the quantum equivalent of a space-time tunnel, and it would mean that wormholes are not rare exotic structures that might or might not exist somewhere in the cosmos. They are ubiquitous. They are the fundamental connective tissue of the universe. Every time two quantum particles become entangled, they are joined by the tiniest possible wormhole. The universe is not smooth. It is woven together by an invisible web of microscopic tunnels, threading through every point in space, connecting everything to everything else, at a scale so small that we have never directly observed it, but whose effects we measure every day in quantum physics laboratories around the world. This idea is still theoretical. It has not been proven, but it is taken seriously by serious physicists. And it suggests something that is, when you sit with it quietly, one of the most breathtaking ideas in the history of human thought. The universe may be connected in a way that goes far deeper than gravity, far deeper than light. At the most fundamental level, things that are separated in space may be connected not despite their separation, but through it, through tunnels that are the very building blocks of space itself. We paused at the edge of something extraordinary. Let us now walk into it. The idea that wormholes and quantum entanglement might be the same thing, that ER equals EPR, is one of the most ambitious proposals in physics since Einstein himself. And to understand why it matters, we first need to understand what quantum entanglement actually is. Imagine two particles are created together in a process that produces them as a pair. Their properties are perfectly correlated. If you measure the spin of one and find it pointing up, the other will always be found pointing down, no matter how far apart they are when you make your measurements. This much has been known since the 1930s. Einstein found it deeply troubling. The implication seemed to be that measuring one particle instantly affected the other, no matter how great the distance. And instant, in Einstein's universe, is a profound problem, because special relativity says that nothing, not even information, can travel faster than light. Einstein suspected there was a hidden explanation. Perhaps the particles simply had their properties predetermined from the moment they were created, like hidden instructions carried in a suitcase. The measurements would reveal those instructions, not create a mysterious, instantaneous influence. This is known as the hidden variables interpretation of quantum mechanics. And in 1964, physicist John Bell showed that it was testable, that you could design an experiment to distinguish between the hidden variables hypothesis and the standard quantum mechanical description. When those experiments were run, first by Alain Aspect in the 1980s, then by progressively more precise measurements over the following decades, the results were clear. Hidden variables were wrong. Standard quantum mechanics was right. The correlations between entangled particles were real, stronger than any hidden variable theory could produce, and they appeared, by every measurement we could make, to be instantaneous. But here is the thing. While the correlations are instantaneous, they cannot be used to send information faster than light. When you measure your particle, you get a random result, up or down, and only by later communicating with the person who measured the other particle, using ordinary, slow light-speed communication, can you discover that your results were correlated. The entanglement does not let you control what you see. It only guarantees that what two people see will be correlated in a way that exceeds all classical explanation. For decades, physicists accepted this mystery as a brute fact. Entanglement was real. Its implications were strange, but it could not be used to transmit information. So, perhaps it was not so alarming after all. It was simply a feature of quantum mechanics that lacked a satisfying explanation. And then came Maldacena and Susskind's proposal. Their insight was this: if two entangled particles are connected by a microscopic wormhole, then the correlations between their measurements are not mysterious at all. The wormhole provides a genuine geometric connection between them, a connection that exists below the level of space as we normally understand it. The particles are not sending signals to each other. They are part of the same extended geometric structure. The implication is that what we call space may not be fundamental at all. Space, the smooth, continuous background in which everything occurs, may be an emergent property. It may be built up from the collective effect of enormous numbers of entangled particles, each pair connected by a microscopic wormhole. If this picture is correct, space is not a stage on which events occur. Space is a consequence of entanglement. Space is a byproduct of the quantum connections between all the particles in the universe. This idea goes by the name entanglement builds spacetime, and it is one of the most actively researched frontiers in theoretical physics today. What happened next in this story surprised even the researchers working most closely on these ideas. In 2019, a remarkable experiment was proposed, and subsequently, in various forms, begun to be tested. The experiment, called the Traversable Wormhole Experiment, was not an attempt to build a real wormhole in the laboratory. It was something conceptually even more interesting. Using a quantum computer, a machine that manipulates quantum states to perform calculations, researchers were able to create a quantum system that behaves according to the mathematics, exactly like a wormhole in a simplified model of spacetime. They could encode information in quantum states on one side of the system, and that information would appear through purely quantum processes on the other side, in a manner that the mathematics of the model described as passing through a wormhole. In 2022, a team of researchers from Caltech, MIT, and other institutions published results of such an experiment, performed on a quantum processor developed by Google. They created two entangled quantum systems, and then manipulated them in a way that was mathematically equivalent, in their simplified model, to sending information through a wormhole. The information appeared on the other side. The news spread quickly. Headlines declared, "Scientists create first wormhole in a lab." This was slightly misleading. No actual wormhole was created. No actual tunnel appeared in physical space. But the quantum information traveled through the system in a way that was precisely described by the mathematics of a wormhole. Whether this constitutes a real wormhole depends on how you define real. In physics, A theory is real if its mathematical description correctly predicts the behavior of physical systems. And in this limited, simplified model, the mathematics of wormholes correctly described what the quantum computer did. The universe may be keeping its deepest secret, that the division between quantum and gravitational, between the small and the large, the particle and the cosmos, may be an illusion. They may be the same thing, described in two different languages, and wormholes may be the place where those two languages meet. There is a question that has haunted astronomers since the moment we first pointed our radio telescopes at the sky and realized, with a slow and growing wonder, that the universe is vast beyond imagination. If the cosmos is so large, if there are so many stars, if the probability of life arising is even remotely plausible, then where is everyone? This question has a name. It is called the Fermi paradox, after the physicist Enrico Fermi, who, during a lunch conversation in 1950, reportedly paused and simply said, "But where is everybody?" The universe is approximately 13.8 billion years old. Our solar system is only 4.6 billion years old. That means there were billions of years before the Earth even formed, billions of years for other civilizations to arise, develop technology, and spread across the galaxy. If even a single civilization in all of that time had developed the ability to travel between star systems, even slowly, even at a tiny fraction of the speed of light, they could theoretically have colonized the entire Milky Way within a few 100 million years. A number that sounds large but is less than 2% of the age of the universe. We see no evidence of this. The sky is silent. The radio frequencies are empty of artificial signals. No probe, no artifact, no megastructure has been detected orbiting any star we have observed. The great silence. And here is where wormholes enter the story in a way that is both fascinating and slightly unsettling. If traversable wormholes are possible, if some advanced civilization somewhere in the universe's long history had the technology to construct or stabilize one, then interstellar travel would not require traveling at high speeds over long distances. It would require building a door, a single door leading from one star system to another. Scientists soon discovered that this possibility actually sharpens the Fermi paradox rather than resolving it. If wormholes are possible, the question becomes even more acute. Not just, why aren't we receiving radio signals from other civilizations? But, why isn't there a wormhole in our solar system? One possible answer is that we simply haven't found it yet. The solar system is large. We have only begun, in the last few decades, to survey it systematically with instruments sensitive enough to detect subtle gravitational anomalies. A small wormhole, mouth perhaps the size of a building or a city, could be drifting somewhere in the outer reaches of the solar system, in the cold dark beyond the orbit of Neptune, and we would not know. Another possible answer is that wormholes, even if constructible in principle, are so difficult to build that no civilization in the history of the observable universe has yet managed it, that the energetic requirements, the need for enormous quantities of negative energy, represent a technological threshold so high that it has never been crossed. This would suggest that wormhole-capable civilizations, if they exist, are extraordinarily rare, perhaps non-existent so far in cosmic history. And in that case, we may be among the first, if not the first, to even seriously consider the possibility, a thought that is simultaneously humbling and exhilarating. Yet another mystery emerged when some researchers began to ask, what if the Fermi paradox is not a problem to be solved, but a clue to be interpreted? What if the Great Silence tells us something fundamental about the nature of intelligent civilizations and their relationship to the cosmos? One of the more thought-provoking suggestions, and it is just a suggestion, not a scientific theory, is that civilizations, as they advance, may turn inward rather than outward. That as technology becomes more powerful, the richest environments for experience may not be found in the physical universe at all. That a sufficiently advanced civilization might choose to inhabit virtual realities, or quantum computations, or nested simulations of their own creation, rather than bothering with the slow, cold, radiation-filled business of exploring physical space. In this picture, the Great Silence is not the sound of an empty universe. It is the sound of everyone having gone somewhere else, somewhere inside, somewhere we cannot see because we're still looking outward. Whether wormholes play a role in this story, whether they might be built and then used, and then abandoned as civilizations discovered something even more compelling, is a question that carries us to the very edge of what physics and philosophy together can say. What happened next in the recent history of astronomy provided a small but tantalizing piece of the puzzle. In 2019, the Event Horizon Telescope Collaboration, a network of radio telescopes spanning the entire Earth, captured the first direct image of a black hole's shadow, the object at the center of the galaxy M87, a giant elliptical galaxy 55 million light-years away, a black hole of 6.5 billion solar masses. The image was a perfect circle of darkness surrounded by a glowing ring of heated plasma. It matched with extraordinary precision the predictions of general relativity. And here is what that confirmation means for wormholes. General relativity, validated once again to extraordinary precision, is the same theory that predicts wormholes. Every successful test of general relativity is, in a quiet way, a confirmation that the mathematical universe in which wormholes exist is the correct one, not proof that wormholes exist, but confirmation that the rules of the game are the rules that allow them. The universe plays by rules that permit wormholes. It plays by rules that permit time travel. Whether it has chosen to include those features in its actual implementation, that remains the question. And it is one of the most beautiful questions we have ever asked. Let us set aside the theoretical architecture for a moment, the mathematics, the exotic matter, the quantum entanglement, and let us simply ask, if a traversable wormhole were available to you, right now, a stable, safe, human-passable tunnel between your corner of the universe and somewhere impossibly far away, what would actually happen? what would you experience? This is not entirely speculative. Physicists have worked through the details, and some of those details are surprising. First, the approach. From far away, as we have already described, the wormhole would look like a sphere. But as you drew closer, say, approaching at a comfortable spacecraft speed, not relativistic, but fast enough to cover the distance to the wormhole's mouth in a reasonable time, you would begin to notice subtleties in the visual field. The star field around the wormhole would be distorted. Stars near the edges of the wormhole's shadow would be displaced from their true positions. Their light, curving around the wormhole's gravitational structure, would arrive at your eye from a slightly different direction than the star's actual location. This is the same gravitational lensing that astronomers observe around massive galaxy clusters, where background galaxies are stretched into arcs and rings by the intervening mass. But around a wormhole, the lensing would have a different signature, a distinctive circular symmetry unlike anything produced by ordinary mass. If astronomers knew what to look for, they might be able to detect wormholes this way, not by seeing the wormhole directly, but by seeing the characteristic distortion of background objects around it. Some papers in the astrophysics literature have actually proposed searches for exactly this signature, systematic scans of the sky, looking for circular gravitational lensing patterns, inconsistent with known massive objects. None have been found, but the searches have not been exhaustive. As you approached the wormhole mouth and entered the transition zone, the region where the geometry of space-time begins to curve significantly, you would feel something. Not pain, not discomfort in the way that acceleration causes discomfort. Something more subtle, a gentle tidal force, a slight difference in the gravitational pull on different parts of your body. If the wormhole were large enough, tens of meters across or hundreds, this force would be so small as to be imperceptible. But if the wormhole were small, barely large enough to pass through, the tidal forces near its throat might be measurable. Not life-threatening, but noticeable. A sense of being gently stretched and compressed in alternating directions as you moved through the curved geometry. Scientists soon discovered that the sensation might be described most accurately not as physical discomfort, but as a kind of perceptual strangeness. Your sense of direction, your vestibular system, the biological apparatus that tells you which way is down, which way you're moving, would receive conflicting signals as you passed through the non-Euclidean geometry of the wormhole's throat. Your eyes would not help you interpret it. The visual field inside the wormhole throat is, according to the physics, fundamentally non-intuitive. Not dark and not light in any ordinary sense. The light that fills the interior is a mixture of photons traveling from both ends of the tunnel simultaneously, from where you came and from where you are going, blended and distorted by the curved geometry into patterns that have no equivalent in ordinary experience. Some physicists have tried to calculate exactly what it would look like. The most comprehensive visual simulations, produced by computational astrophysicists using full numerical general relativity, show a tunnel-like appearance with a sphere of distorted external imagery visible at each end. But the walls of the tunnel are not smooth. They are defined by the trajectories of light rays, which, in the strongly curved interior geometry, form complex patterns of rings and arcs that change as you move. It would, quite simply, not look like anything you had ever seen. And then you would reach the throat, the narrowest point of the wormhole, where the geometry is most extreme. And then you would be through the other side. What happened next would depend entirely on where and when the other end of the wormhole opened. If it opened in a distant region of our own galaxy, say 10,000 light-years from Earth, toward the galactic center, you would emerge into a sky absolutely nothing like the one you left. The star density near the galactic core is thousands of times higher than in our neighborhood. The night sky from that vantage point would be blazing. The Milky Way not a faint band, but a wall of light filling the entire sky, so bright that true darkness might not exist at all. Thousands of stars visible to the naked eye, many of them giants, many of them young and blue hot. A sky so different from ours that it would take time, quiet time, still time, to absorb what you were seeing. And if the wormhole had caused time displacement, if one of its mouths had aged differently than the other, you might also be in a different when. You might have emerged into the same galaxy, the same star neighborhood, but thousands of years in the future, or the past. The stars would be the same. Stars live for millions of years, so the difference would not be obvious at first. But subtle things would be different. The Earth, seen from here, would show light that left it thousands of years ago, light from a time before our history. There is a peculiar beauty in this. If you emerged from a wormhole that had time displaced you into the past, and if you aimed a powerful enough telescope back toward the solar system, you would see Earth as it was in a different era, not the planet we know, a different world, a previous world. You would be a witness to your own history from a vantage point outside it. The answer raised an even bigger question. If you could witness your own history, if you could see it, but not touch it, not interact with it, what would that do to your sense of who you are? What would it mean to see your own civilization from the outside, from a distance so great that you could do nothing but watch? This is not a question physics can answer. It is a question for philosophy, and perhaps for the quieter parts of your own mind. And it is exactly the kind of question that a journey through a wormhole would, if such a journey were ever possible, force upon us. We have traveled a long way tonight, through equations and paradoxes, through the geometry of black holes, and the strangeness of quantum entanglement, through the visual landscape of a journey no human has ever made. And now we have arrived at the question that underlies all of this, and which is perhaps the most honest question of all. Is any of this real? Not in the sense of theoretical reality. We have established that wormholes are mathematically consistent, that they do not violate known laws of physics, that the equations clearly permit them. What we are asking now is something different. Could a wormhole actually be traversed by a human being in the actual physical universe, not in a model or a simulation, but in the real, material, indifferent cosmos in which we actually live? To engage seriously with this question, we need to understand the scale of the obstacles. The first and most fundamental is the exotic matter problem. As we discussed, keeping a wormhole open requires negative energy density, The quantity of negative energy required for a wormhole large enough for a human being to pass through is, by the most optimistic estimates, comparable to the energy output of a star. By less optimistic estimates, it might require energies comparable to the total mass energy of a planet or multiple planets in a negative form. Humanity, at our current level of technological development, generates approximately 2 × 10 circumflex 13 watts of power across all human civilization combined. The energy required to maintain a traversable wormhole exceeds this by many, many orders of magnitude. This does not mean it is impossible. Stars exist. The energy of a star is not beyond the physical universe's capacity. It is simply the case that we, humanity in the 21st century, are nowhere near capable of harnessing it in the way required. A thought experiment. Imagine a civilization 1 million years more advanced than ours. Not 1 billion years, just 1 million. 1 million years ago on Earth, our ancestors were simple stone tool makers, just beginning to develop language. 1 million years of technological development represents a span of time we have difficulty even imagining in terms of what it might produce. Would a civilization 1 million years more advanced than ours be capable of constructing a traversable wormhole? We honestly do not know. We cannot predict the technological capabilities of civilizations vastly more advanced than our own. But we can say this: there is nothing in the known laws of physics that says such a civilization could not do it. The obstacles are engineering obstacles. Formidable, almost beyond imagination. But engineering. Yet another mystery emerged when physicists began to consider the second major obstacle: stability. Even if you could create the necessary negative energy and construct a wormhole, there remains the question of whether it would stay open. The theoretical analyses suggest that wormholes may be inherently fragile, that small perturbations or the quantum effects of radiation passing through them could cause them to collapse faster than anything could cross. This is particularly problematic because of the quantum energy conditions. One of the most important results in wormhole physics, due to the work of Ford and Rosen in the 1990s, states that while quantum mechanics permits negative energy, it constrains how much negative energy can exist in any given region, and for how long. Specifically, the larger the negative energy you create, the shorter the time it can be maintained. This is called the quantum interest conjecture. It suggests that nature essentially charges interest on negative energy. You can borrow it, but you must pay it back quickly. And the more you borrow, the faster the repayment is required. For wormhole engineering, this is a significant constraint. A wormhole that needed to remain open for years or decades. To be useful for travel would require a continuous supply of negative energy, not just a one-time injection. The engineering would need to not just create the negative energy, but maintain it indefinitely. This makes the challenge more complex, but still not forbidden. What happened next in the theoretical development of wormhole physics was, in a way, both sobering and clarifying. In a series of papers in the 2010s and 2020s, various groups of physicists began to analyze wormholes in the context of holography, the principle derived from string theory and black hole thermodynamics. that suggests the information content of a three-dimensional region of space can be fully encoded on its two-dimensional boundary, surface. In holographic theories, wormholes have a very specific and constrained behavior. They are not simple geometric tunnels through space-time. They are entangled quantum systems whose geometric appearance, the tunnel itself, is an emergent property of the entanglement. And in these theories, traversable wormholes are not just geometrically special. They preserve unitarity, the quantum mechanical principle that information is never truly destroyed. This is significant because it connects the wormhole question to one of the most important unsolved problems in modern physics: the black hole information paradox. When matter falls into a black hole, and the black hole eventually evaporates through Hawking radiation, is the information encoded in that matter preserved or destroyed? Stephen Hawking originally argued that it was destroyed, a conclusion that contradicts quantum mechanics. But recent work, including the holographic treatment of wormholes, suggests that it might be preserved after all. The implication is striking. Wormholes may be not just theoretical curiosities or potential travel shortcuts, but fundamental elements of the mechanism by which the universe preserves information. They may be the hidden channels through which the quantum mechanical principle that information cannot be destroyed is upheld, even in the extreme environment of a black hole. The universe in this picture keeps its records through wormholes. Every black hole that forms, every particle that falls in, every atom that is compressed beyond all possibility of ordinary existence. The information about all of it may be preserved and transmitted through microscopic wormhole connections woven into the structure of space itself. And this brings us to perhaps the most profound implication of wormhole physics, which we have been approaching throughout this entire journey, and which we are now ready to face directly. We have been building, slowly and carefully, toward an idea that changes everything. Not everything in any dramatic, sensational sense. Not with noise or urgency, but quietly, the way a shift in understanding sometimes arrives, not like a thunderclap, but like the gradual brightening of dawn. So gradual you can't say exactly when it happened, only that at some point the sky was dark, and now it is light. The idea is this: space itself may be made of wormholes. Let us unpack what this means. In the early years of quantum mechanics, physicists discovered that matter, solid, tangible, apparently continuous matter, was not actually continuous at all. The table, the chair, the floor beneath your feet, all of it was composed of atoms, and atoms were mostly empty space, and within the atoms were nuclei made of quarks, and the quarks themselves were not solid objects but quantum fields, probability waves, things that defied every intuition built up over a lifetime of touching and being touched by a macroscopic world. Matter was granular. It had an underlying structure invisible to ordinary observation. What the work on wormholes, quantum entanglement, and holography is now suggesting is something analogous. Space, the smooth, continuous dimensioned fabric in which all events occur, may also have an underlying structure, a granularity, and that granularity may consist, at the Planck scale, of quantum wormholes. Each point in space, connected to every other point, by a vast web of microscopic quantum wormholes. The apparent smoothness of space, the fact that it seems continuous, that you can move in any direction at any scale and find more space, would then be an illusion, in the same way that a smooth piece of paper is an illusion when you look at it under a powerful enough microscope and find that it is a complex three-dimensional network of tangled fibers. Space is woven from wormholes. If this is correct, and it is one of the most actively explored hypotheses in theoretical physics today, then the implications extend in every direction. It would mean that the fundamental unit of the universe is not a particle, not a string, not a brain, but a connection, a relationship, a tunnel between two things. The universe, at its most basic level, would be made not of stuff, but of links, not of objects, but of bonds. This is a shift in metaphysics so profound that it is difficult to fully absorb. We are accustomed to thinking of reality as composed of things, particles, waves, fields, things that exist at locations, that have properties, that interact when they come close enough together. But if space is made of wormholes, then the notion of location becomes secondary. What is primary is not where something is, but what it is connected to. The universe is a network, a web, a vast, intricate, self-sustaining system of relationships, and the things we perceive as distances, the vast emptiness between stars, the unfathomable gulfs between galaxies, are not truly empty or truly vast. They are full of connections, full of microscopic wormholes linking every point to every other point in a way that underlies and generates the apparent geometry we observe. Scientists soon discovered that this picture, if correct, might resolve one of the deepest puzzles in modern physics. Why is there something rather than nothing? Why does space exist at all? In the wormhole entanglement picture, space does not exist independently of the matter and energy within it. Space is generated by the entanglement of quantum fields. The more entanglement, the more space. A completely disentangled system, a pure quantum state, would not generate any space at all. It would not have a geometry. It would simply be a quantum state with certain properties. Space, in other words, is what happens when things are quantum mechanically correlated with each other. Space is the geometry of relationship. This is a stunning idea, and while it remains theoretical, while we do not yet have the full mathematical framework to test it rigorously against observations, it has motivated some of the most exciting work in theoretical physics of the past 2 decades. The answer raised an even bigger question. If space is made of entanglement, and entanglement is equivalent to wormholes, then what happens to space when entanglement is broken? When a quantum system decoheres, when its delicate quantum correlations are disrupted by interaction with its environment, does the space around it change? In ordinary circumstances, the effect would be immeasurably small. We are not going to see space dissolving because of quantum decoherence in a laboratory. The scales are completely different. But in extreme conditions, near the singularities of black holes, or in the very early universe, decoherence effects might be significant, might actually affect the geometry of space-time. This could be part of what happens near a black hole singularity. As matter falls in and the conditions become extreme, quantum correlations, and thus the wormhole fabric of space, might be disrupted in ways that general relativity, which treats space as smooth and classical, cannot capture. And perhaps the resolution of the information paradox, the question of whether information is preserved or destroyed in a black hole, is precisely the story of how the wormhole fabric of space adjusts to preserve those quantum correlations, even as everything else falls apart. What we are describing, in outline, is a universe that is not a cold, mechanical structure of particles and forces, but something more like a vast, self-correcting network of relationships, a system that maintains its own coherence through connections that are invisible at ordinary scales, but fundamental at the deepest level. Something that, if you step back far enough and let your mind relax its grip on conventional intuition, looks less like a machine and more like an organism. Not a biological organism, but something with its own kind of wholeness, its own kind of interconnectedness. A universe that is, at its most fundamental level, woven together, and wormholes, these strange, beautiful, hypothetical tunnels through space-time, are the threads of that weaving. We have come a long way tonight. We began in the dark, floating between galaxies, with a single question: what if there were a shortcut? We have traveled through the mathematics of Einstein and Schwarzschild, through the strange geometries of black holes and rotating spacetimes, through the physics of negative energy and quantum foam. We have stood at the edge of the time travel paradox and looked into its depths without flinching. We have watched wormholes and quantum entanglement converge into a single picture. We have considered the possibility that the universe is not a collection of objects, but a web of connections, and that space itself may be woven from the tiniest possible wormholes, threading through every point in existence. And now, at the end of this journey, I want to leave the mathematics behind. Entirely. I want to sit here with you, quietly, and simply feel the weight of what we have been exploring. Because there is a feeling that comes, if you let it, after spending time with ideas this large. It is not quite awe, though awe is part of it. It is not quite peace, though peace is part of it. It is something more like perspective. The universe is 13.8 billion years old. In those 13.8 billion years, from a mere infinitely hot and dense beginning, space itself has expanded until it now encompasses a volume containing at least 2 trillion galaxies, 2 trillion collections of hundreds of billions of stars each. And within each of those stars, nuclear fires burn that have forged the atoms of carbon, oxygen, iron, and every other element from the raw hydrogen of the early universe, including the atoms of which you are made. You are not in the universe. You are made of the universe. The carbon in your cells was forged in stars that died billions of years before the sun formed. The iron in your blood was created in the final explosive deaths of massive stars, supernovae that scattered their contents across space for millions of years before gravity drew them back together into new systems, new planets, new life. You are, in the most literal and physical sense possible, a piece of the cosmos, that has become aware of itself. And tonight, that piece of the cosmos has been sitting quietly and asking whether the cosmos contains wormholes, whether the fabric of space is tunneled, whether there are shortcuts through time and space woven into the architecture of everything, whether the universe is, at its heart, more connected than it appears. I find something deeply comforting in the possibility that the answer might be yes, because we live in a time of distances. Not just the distance between stars, those are too large to fully feel, but the smaller distances, the distance between people, the distance between who we are and who we hoped to become, the distance between the life we are living and the life we imagine. And there is something quietly beautiful about a universe that, at its most fundamental level, may refuse to honor those distances. That may contain, woven into its geometry, mechanisms for connection that operate beneath and beyond ordinary space. That may be structured, at the smallest scale, as a web of relationships. A network of wormholes that binds every point to every other point in ways we have barely begun to understand. A universe in which nothing is truly isolated, in which every particle, every photon, every atom is connected to everything else by channels too small to see, but real. We do not know if traversable wormholes exist. We do not know if any civilization has ever found a way through the engineering challenge of exotic matter. We do not know what lies on the other side of a black hole's singularity, or whether the quantum phone of space is truly riddled with microscopic tunnels. But we know something that is, in its own way, equally remarkable. We know that we are the kind of creatures who ask these questions. We know that the same material universe that produced stars and black holes and vast cosmic voids also produced, in at least one small corner of an ordinary galaxy, creatures with the capacity to wonder about it, to build telescopes and point them at the dark, to write equations and follow them wherever they lead, to sit in the quiet of the night and ask, what else is out there? What else is possible? That capacity, the capacity for curiosity, for wonder, for the particular kind of attention that turns toward a mystery and says, I want to understand this, not because it will help me tomorrow, but because it is beautiful. That capacity is one of the universe's stranger gifts, and wormholes of all the mysteries in physics may be the most fitting symbol of what that gift makes possible. They are the idea of connection across impossible distance, the possibility of shortcuts through the constraints that ordinary space and time impose, the suggestion that the rules of the universe, while real and binding, may contain within them doorways that we have not yet found. Perhaps somewhere in the cosmos, there is a civilization that found those doorways long ago. Perhaps they stand at the entrance of a wormhole the way we stand at the entrance of an ocean, knowing it is vast, knowing it is full of things they cannot see, but stepping in anyway, carried forward by the irresistible pull of what might be on the other side. Or perhaps the wormholes are there, natural features of the universe's geometry, never used, never found, simply waiting, patient in the way that only something with no awareness can be patient, simply existing, connecting points A and B across 10,000 light years, unobserved, in the dark between stars that have been burning for billions of years without any witness. In either case, they are there in the mathematics, in the equations that have predicted black holes, gravitational waves, the bending of light, all of which were once theoretical curiosities and are now confirmed features of observable reality. The mathematics says the universe contains these structures, and the universe, as far as we can tell, is honest. So tonight, as you drift towards sleep, if that is where this journey finds you, let your mind rest somewhere quiet, somewhere between galaxies maybe, in the dark, with the stars spread out in every direction, and somewhere ahead, a faint, luminous circle, a sphere of distorted light, hanging in space, a door. It may lead to a place 10,000 light years away. It may lead to a moment 1,000,000 years ago, or 1,000,000 years from now. It may lead to a part of the universe that no human eye has ever seen. Or it may simply be the door to sleep, to the deep, quiet, dreamful rest that comes after a journey well taken. Either way, you have traveled far tonight, and the universe, in all its incomprehensible size and strangeness, has been patient company. It will be here when you wake. It always is. Good night.